Hey guys, this is Mrs. Tran-Bloom. We are starting our new unit here. So 3.1 says derivative of a function. So our first definition is the average rate of change. This is indeed a review of last unit, okay? So the average rate of change is when 2 points are known. Now, if you guys remember last unit, aka this was also thought of as a slope of a secant line. So the formula of this slope is the change in y divided by the change in x. And last unit, we were using f of b minus f of a divided by b minus a. Or in algebra 1, it is okay to go y2 minus y1 all over x2 minus x1. Any one of those is okay by me. Now, we also talked about the definition of instantaneous rate of change. Now, remember, the instantaneous rate of change is when 1 point is known. Well, so how do you find the slope when 1 point is known? This is, remember, we talked about this is when looking at the graph of the function, is the slope of the tangent or tangent line, because in your book sometimes they said find the tangent, which is the same thing as find the tangent line. Okay, so tangent line at a point known, let's call it A, and the y value would obviously f of a, and a nearby point. Let's say that we don't know where that is, so we will give it an unknown x. So that means its y value will be f of x. Okay, so we have 2 points here. We are going to have 1 point that's given to us. And remember, we talked about, hey, let's pick a nearby point. Let's call it whatever, x, comma, f of x. Now, last unit, okay, so last unit, you were given a formula. The limit as h approaches 0 of f of the known point a plus h minus f of a, whatever that algebra 1 value may be, divided by h, and we talked about h is the distance, right, from a, or to a, however you want to think of it. Okay. Now, this unit, we are going to add a similar formula. So, new formula. We are going to use the limit as our nearby point, which is x, approaches our given point, which is a. So if our nearby point is approaching our given point, then obviously the closer the point we pick, right, if it approaches our given point, then the distance would be very minimal. So the concept is still the same. And so because we're picking, I mean the y value will be f of x minus f of a all over x minus a. Okay, so this means the point we picked, which is x comma f of x, okay, is approaching the given point a comma f of a. All right. Now, this in calculus, guys, is referred to as the derivative. Okay. And notation, guys, we do have the notation to the derivative. Okay, so the notation is f, and then there's this prime of a. I'm going to spell it out. Ready? This is red. This is red. F prime of a, or derivative of f at, ooh, that's too close together, at point A. Okay. All right, formal definition of the derivative. This is used to find the derivative of f as a completely separate function. Okay, so here we go. The derivative of the function f with respect to the variable x is the function f prime whose variable x is, ready? F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. We have seen that before, would you agree? Provides that the limit exists. Now the domain of f prime is in the domain of f, which means, guys, the domain of f prime, the domain of f prime may be smaller than domain of f. Okay. Now let's go back and do, how about this? Can we do a bullet right? Oh my goodness, what happened? Okay, can we do a bullet right here? That's number one. Number two will be the domain, and then one more bullet right there. Okay. If f prime of x exists, we say that f is differentiable at x. So this is a word that we want to know. So a couple highlights here, guys. The formal definition of the derivative, you have to know this definition. Okay, it doesn't go away at all, ever. So make sure this is highlighted. It is the same exact formula as last unit. And then we do want to know the domain of f prime. It's in the domain of f, which may be smaller than the domain of f itself. Okay. Now, if f prime exists, then we say it's differentiable at x. Another definition for derivative. This is a second definition or an alternative definition. The formal definition you must know. There's no ifs, ands, or buts about it. Okay. Now sometimes it is easier to use this alternative definition here, and in your book it will state use the other definition of derivative or use a formal. So make sure you guys read those directions very carefully. All right, so the second definition of derivative. derivative of f at a point, let's call it A, is f prime of A equals the limit as x approaches A of f of x minus f of A all over x minus A, provides that the limit exists. Okay, now students, use this formula. Use this when you know the point. Okay, use the formal definition when you don't know the point. Example 1 says, apply the first two definitions of a derivative to the function f of x equals x squared plus 3x. So we are going to get to try both derivative definitions. So here's the formal definition. The formal definition, students, says f prime of x is limit as h approaches 0 of f of x plus h minus f of x all over h. Ready? We are going to do the other one on this side. The alternative definition is f prime of x equals the limit as our given point. Okay, so as x approaches A, so x is a nearby point, we want it to get really, really close to the given point of f of x minus f of A all over x minus A. All right, let's work this out. Ready? Get set, go. All right, f prime of x equals the limit as h approaches 0. We're just going to focus on this side first. We do want to calculate f of x plus h. As you guys know, every time we see an x, we do want to input in x plus h, okay? So we have two locations of x's over here. So one is the square. Whoa, oh my goodness, every time I pinch it in, it does that. Okay. So one is going to be something square, and then plus 3 times something. Now minus f of x, okay? Minus f of x, meaning that, hey, f of x is given to you already. F of x was given to you as x squared plus 3x. So we want to minus the entire f of x. So that's x squared plus 3x. So that is f of x right there. So for f of, this is the part where I feel like some of you are still struggling. Whenever you guys are evaluating f of x plus h, if you see an x in the original, you're going to put in x plus h. If there are multiple x locations, you put it in for every time that you see an x in the original, okay? Then just from there, slowly FOIL that out. So the limit as h approaches 0, FOIL the first quantity, that's going to be x squared plus 2xh plus h squared. Then distribute your 3x here plus 3h, distribute the minus sign, so minus x squared minus 3x all over, whoops, all over h on the top as well. My bad, guys. Okay, then from here, see if we can cancel anything out. Ready? We can cancel one of those, and now we will try to factor out the h from the numerator. So we are going to end up with 2x plus 1h here, then just plus a 3 all over h. Those two will cancel. Remember, h is approaching 0. So by substitution, I'm going to write this down. Okay, so by substitution, 0, we have 2x plus 3. So students, when it's all said and done, f prime of x is plus 3. Okay, so this is the derivative of our original equation of x squared plus 3x. Remember, the derivative is the slope. So this equation represents the slope of all given values of x, okay? Now we are going to try to use the second formula here to see what's going to happen. We are going to, remember, we don't know, we're not giving an a value, so we're going to assume an a value will still be an a value. So x approaches a, f of x, students, is this original equation, so that's going to be x squared plus 3x minus, to evaluate f of a, every time you see an x, we are now going to do a squared plus 3a all over x minus a. Then from here, we are going to slowly work out the algebra. So x squared plus 3x minus a squared minus 3a all over x minus a. Here is when we are going to use some algebra manipulation. And you know, math is amazing. Okay, here we go. X squared, I'm going to regroup the square term together. And I'm going to write the 3x and the 3a together. After that, we are going to try to factor out these two and factor those out. So factor by grouping, okay? So the limit as x approaches a. So the first two groups, guys, that's a difference of two squares, okay? So we're going to go, okay, difference of two square, x plus a times x minus a. The second two group, we can take out a 3 because that's the GCF. We now have x minus a left, all over again, x minus a. Now, as you can see here, we can cancel this and this and this because technically, if you want to see another step here, we'll do another step here. Technically, from there, we can factor out x minus a because they have that in common. Then we are ending up with an x plus a plus 3, okay, all over x minus a. So if you want to wait until here to cancel, that's okay too. But as you can see, now it says if x is approaching a, okay, again, if x is approaching a, and by substitution, right, every time we see, if let's pretend that this is a value of 5. So if x is approaching 5, every time we see our x, we need to plug in 5. But we don't know what a is since it didn't really give it to us. So every time we see our x, we will plug in an a. So a plus 3 all over 1, which is no longer there. So students, this is 2a plus 3. Now this is when we have x equals to a, okay? So the derivative, so f prime of x is 2a plus 3. Now example 2 says apply the formal definition to our function f of x equals sine of x, okay? So we are going to write the formal definition first. F prime of x, that means the derivative of function f, is the limit as h approaches 0 of f of x plus h minus f of x all over h. This is just the definition. I'm just writing it down for you. Now let's work it out together. So by definition, the limit as h approaches 0 of f of x, that means I now have sine of x plus h, okay, minus sine of x all over h. And I hope that you remember your sum and difference formula. So here we go, sine of x cosine of h, okay? Then I'm going to add cosine of x sine of h, and then just drop the sine of x back all over h, okay? Then continue, limits as h approaches 0. I'm going to try to factor this out because right now if I plug in h, that's not going to work very well. But I do see that this right here has something in common, so I'm going to try to put those two together as one group, okay? Cosine of h minus sine of x. I'm going to put that together as one group, and then I'm just going to drop down everything else that's not in that group. So now all over h, which is limit as h approaches 0 Now I'm going to take out the sine of x, okay? I'm left with cosine of h minus 1 all over h, okay? But here's what I'm also going to do. Based on our limit properties, I'm allowed to add limit as h approaches 0 of cosine of x, okay, times limit as h approaches 0 sine of h. What am I doing here? I'm just using the limit properties and break these into pieces, okay? So keep in mind that these are all still all over h, okay? So this whole thing is all over h, but I don't want to write all over h like that, right? I just want to write 1 here, okay? So technically, you know what? Let me just write that next step, all over h here. And this is technically, both of these are still all over h, okay? So, you know what? Let me just write that. Let me just insert that step in the middle so that way you're not confused. So, since I broke this up, technically this is really just this, okay? All over h, okay? Well, next I'm going to write limits as h approaches 0. I'm going to write sine of x all over 1, okay, times cosine of h minus 1 all over h that way. Then I will break this up, limits at h approaches 0, and then same thing with this, I can break it up as only one of it, right? Put sine of h over h times cosine of x over 1, okay? So you can always do that using our properties of limits. So what's happening? As h approaches 0, remember, this is one of the properties you were supposed to know as h approaches 0, okay? That property is what? As h approaches 0, that is 0, okay? And you're supposed to know this. This is what? This one over here is 1, okay? So, well, I have 0 over here. I still have the limit as h approaches 0 of sine of x, right? And over here, I now have 1 times the limit as h approaches 0 of cosine of x. Well, what's going on here is as h approaches, so what's going on is, well, what's going on? I don't know when h is approaching 0, right? 0 times anything is 0. Okay, so over here, this whole thing is going to be 0, right? This whole thing is going to be 0, okay? Because I don't care what this is, right? H approaches 0, it's just not even in this equation. So whatever sine is, okay? So sine times 0 is 0. Over here, well, guess what? This limits right here. The limits as h approaches 0, h is not even in this equation. So cosine the limit of h approaches 0, cosine of x is just cosine of x, okay? So that right here is just cosine of x. So guess what? The derivative becomes just cosine of x, okay? So what do we take from this? The derivative of sine is cosine of x, okay? So the derivative of sine is cosine of x. So keep that in mind. Now, do you have to do this proof over again? No. From now on, if I ask you, what's the derivative of sine of x? You could just write the answer. It's cosine of x. And let's go and graph that out really quickly, okay? I'm going to use our Desmos. Here we go. I'm going to type in sine of x and cosine of x, and then you can tell me what's going on, okay? So we are going to use function sine of x. That will give you this beautiful piece. Next function, let's do cosine of x, okay? Okay, so as you can see, the graphs are definitely different, okay? There's no doubt about that. So how are the derivatives, okay? How are the derivatives the same? Remember, the derivative isn't looking for the derivative is looking for like, hey, what's happening at a particular point, right? So the derivative is talking about, hey, if I move this, okay, if I move this along x, okay, what's going to happen? Okay, so what if I do a little animation for us, okay? So keep in mind the red one is your sine, and then the orange one is your, the colors are changed. The orange one is your cosine. So remember, the derivative is a slope at a point, okay? So, and sine keeps on going forever. So what if I were to find a tangent at every single point, okay? Every single point on the sine curve. So follow that really quickly. And so guess what's happening? Every single point on the sine curve, as we find the slope, guess what's happening? The height makes the value that we can use to graph cosine, okay? And again, the height, okay, or the tangent of sine, okay? So the height or the tangent of sine gives us values that can be used to plot your cosine. That's exactly what's happening. So the derivative of sine is cosine, okay? So that's what this animation is supposed to be, okay? So the tangent at every single point on the sine curve gives us the perfect point to plot out cosine, okay? So that's what's happening there. So as that algebraically, and hopefully the graphing helps a little bit, okay? Oh man, okay, so let's go do this one right here. Example 3, find the derivative of f of x equals 1 over x at x equals 3. So as you can see, this one you know, okay? You know a point, x equals to 3. So I'm not going to use the formal definition. I'm going to use the derivative at a point definition. So first I would like to do is I want to find out what f of 3 is. Okay, so f of 3, let's find out what that is. Let's plug it in. 1 over 3, it's just going to be 1/3. So 3 comma 1/3 is my point. Okay, so formula says f prime of your point, whatever this point is, a, is the limit as x approaches a. In this case, your a is 3, okay? X approaches 3. F of x minus f of 3, because that's f of a, all over x minus 3, okay? So by definition, limits as x approaches 3, which is going to be f of x, which is 1 over x, minus f of 3. I found f of 3 already from here, so I'm just plug in 1/3 minus 1/3 all over x minus 3. I'm now going to find the common denominator for the top. So that's going to be 3x. That means I'm going to multiply this side by 3 and this side by x. Okay, so that's going to be 3 minus x. Okay, divided by 3x. Okay, so this is one of them. So now I'm going to do division this way. And I think some of you will be able to see why I'm writing it that way. Okay, because now if I were to go and multiply by its reciprocal, guess what happens? I'm going to now rewrite negative x plus 3 this way, all over 3x. Divide is now multiplication of its reciprocal of x minus 3. From here, I will factor out the negative, right? So now it's x minus 3 over 3x times 1 over x minus 3. This will help me reduce this right here. So I now have negative 1 over 3x. So the limits, that's x approaches 3 of a negative 1 over 3x. Okay, so as you can see, I'm kind of the end. Now I just have to do is plug in your a or your x really. So at x approaches 3, by substitution, my derivative at this location, it's 3 times 3, which is going to be 1 over negative 1 over 9. Okay, so this is the derivative at a point. In this case, the point is when x is 3. Example 4 in section 3.1. Given the graph of the function below, let's call this function f. Sketch a graph of the derivative of f. Okay, so this is very, very common. So I'm going to make a chart or another grid over here. And please, if you are going, number one, oh, that's so ugly. I don't want you to graph more than 1 or 2 graphs or function in one coordinate plane. Okay, if you have 3, it's just too busy. If you have 2, at least you can label it. So over here, you're given a regular function. Over here, I am going to be graphing the derivative of it. It's called f prime. So what we are going to start with is we are going to identify, okay, identify where your derivative is 0. Okay, so tactics for sketching f prime. Okay, let's start with the first one, easy one. Look for the obvious slopes. Okay, most obvious are when the slope is 0. The slope is 0 means I'm looking at a horizontal tangent. Remember this? We talked about this before in our last unit. Horizontal tangent is when the slope is 0. When are they? If you're giving a graph, the slope is 0. Okay, when is a horizontal tangent? Which is, as you can see, at the vertices. Okay, since I have 2 here, these are them. Now, x is still x. Okay, so x is in f of x is the same as x in prime. Okay, so looks like I'm gonna have x is 1 right here, right? X equals 1, so that's my first one. So what does that mean? Well, when x is 1, the slope is 0, which means f prime is 0. Okay, that's why the tangent is horizontal. Another location is when x, let's just pretend that this is when x equals to -2. So at -2, it's another location that your slope is 0. That's another location that's going to give me a horizontal tangent. That's why this is not labeled f of x anymore. As you can see, this is now labeled f prime of x, okay? Next, what do we do from here? Okay, tactic number 2. Let me just repeat what I just said. Remember x values of f prime is the same as x values in f of x. Okay, so the horizontal values are not changing, it's just the vertical values are changing. Okay, then step 3, just to kind of have an organization, I tend to make a chart. Okay, make a chart using x values. And no, you don't have to follow these tactics. The more you practice, the quicker you will be able to sketch these out. So what's happening is that you have 2 locations, okay, of when f prime is 0. So the first location is x equal to 2, and the second location is x equals to 1. Okay. So what do I do with this? I'm going to make a chart here. Just like that, okay? So I'm going to call this x value, and I'm going to have this f of x. Yes, regular f of x. I don't need a lot of space, and this is f prime of x. And I'm going to call this left. So over here is where I'm going to call left side of x equals to -2, okay? Left side of x equals to -2. Over here is in the middle, because it's in the middle. And over here is on the right side of x is 1. What am I trying to do? As you can see, okay, is this. On the left side of -2, on the left side of -2, is your original function increasing or decreasing? Okay, so as you can see, it's increasing. Because on the left side, the original function f of x is increasing, your derivative is positive. Okay, what do I do with that information? Well, positive means on the left-hand side, which is this right here, positive means I'm above the x-axis. That's what it means, in which now I erase a circle. Okay, so that's what it means. Now, in the middle, okay, in the middle, your regular f of x function, is that decrease or increase? That is decreasing. Okay, what does that mean by decreasing? Decreasing is when the derivative is going to be negative. That's right, that's how they are related. What does that mean? So in between -2 and 1. Negative means I'm below, oh, it looks like a smiley face, below the x-axis. Okay, right now I'm not very picky on the steepness of it. Okay, I'm just looking for above and below. Then what's happening on the right hand side of x equals to 1? That is increasing. Okay, increasing, just like, let me erase this line, increasing, again, that means f prime is positive. Okay, so what does that mean? Positive means I'm above the x-axis. Okay, so the derivative of a cubic, so let me just erase all the stuff I marked here. The derivative of a cubic is a quadratic. Isn't that beautiful? And that's how you need to, that's what you need to do to sketch it out. Again, I'm just going to say it again. I'm just going to ignore the steepness for now. We will talk about that when we get to chapter 4. Okay. Example 5. Sketch the graph of a function f that has the following properties. Okay. Doesn't this remind you of chapter 2 where you have to sketch and then I gave you a bunch of properties again? Kind of like that, but now we're dealing with derivatives. So sketch the graph of a function. Okay, a function means I'm looking for the original, and I'm going to make a coordinate plane, and I'm going to kind of talk to you guys as I go along, or my thought process. Okay, 1i says f of x, okay, has an algebraic value when x is 0, y is 0. So what does that mean? I'm going to go and plot a 0, 0. Okay, so this is what it means by f of 0, y is 0. You have an algebraic value. Okay, 2i says the graph of f prime, the derivative of f, is shown below. Oh my. And then 3i says f is continuous for all x. So that means I cannot, okay? This means I cannot have any holes or infinite discontinuity or what else are we thinking about? Jumps, anything like that, okay? So I'm going to use f prime to finish up the rest of my graphing. So here's the f prime graph, okay? What does that mean? That means, let's look at it. The slope, see this right here? The slope starting from 1, this is when x equals 1, and on, it's always 2. Okay, this is how you read it. The slope is 2 from 1 all the way to infinity. How does that affect your f of x function? Let's go and label this. This is no longer just, so you have to label because you don't know, I don't know what you're trying to graph, okay? Just like the previous example, we were graphing f prime, now we're going backwards. We are trying to graph f of x. So where is 1? Okay, let's make some tick marks. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Well, it says the slope from 1 and on is 2. Well, I'm going to make some dash lines for now, and then later I will erase because I don't want you to think that these are asymptotes. Here's 1, right? X equals 1. From 1 all the way into infinity, the slope is 2, okay? Then let's go to the next line. Let me use a different color. This guy right here in the bottom, okay, this guy right here is saying that the slope from negative infinity all the way to 1, is negative 1, okay? So again, okay, the confusing point right now is when x equals to 1. As you can see, the slope does not exist. See, okay, so this is important right here. I think my computer's frozen, so okay. So I want to pinpoint something really quickly. The slope at 1, as you can see, does not exist, okay? Okay, so the derivative at x equals 1 does not exist, okay? Okay, so let's do it. The slope, okay, from negative infinity to 1 is negative 1. This point is my starting point. It's on the left-hand side of 1. So I need to have a slope of negative 1. What does that mean by slope of negative 1? Go down 1, left 1, right? Down 1, left 1. Or I can go up 1, right 1. Up 1, right 1. That's what it means to have a slope. Up 1, right 1. So here is the dot. These are the dots that I needed to graph f of x, okay? And again, this is pretty confusing, but you kind of need to know how to read your f prime graph. So as you can see, from negative infinity to 1, the graph, this is my f of x function right here, okay? Does it have a slope of negative 1? Sure it does, right? Remember, I just counted it. I went down 1, right 1, or up 1, left 1. So right there has a slope of negative 1. Now let's go from erasing. I need to erase a couple things. It's too busy. Okay. Now let's go from 1 to infinity. The slope, okay, from 1 to infinity is 2. It's positive 2. What does that mean? I'm just going to count. That's all. Up to right 1. Up to right 1. That's what it means by having a slope of 2. You're just counting, okay? There you go. So, all right, the slope does not exist at x equals to 1 because, look, there's a hole. But your condition said that f has to be continuous, okay? So what that means is I need to fill this in. Yes, okay? Let's talk about this. It's filled in, meaning that the slope does not exist at x equals to 1. Why does it? How come the slope does not exist? Because the slope coming from the right hand and the slope coming from the left hand are not the same. One of it is 2 and one of it is negative 1. They're not equal. Therefore, the derivative does not exist. Remember the definition. The derivative, for the derivative to exist at a point, the slope or the limits has to exist, okay? So for this case, it doesn't exist, even though it is a whole, okay? Now, this is slightly different from chapter 2, okay? So in chapter 2, we were not talking about the slope. We were not talking about the derivative. We were not talking about the tangent. In chapter 2, we were just simply finding the limits of f of x at x approaches 1. This exists, okay? This is definitely exists. It is negative 1, okay? But the slope is different from the height, okay? This right here is the height. I want you to understand the difference between the two. This right here is the slope. The limits as h approaches 0 of f of a plus h minus f of a all over h. This right here is talking about the slope of a tangent. Slope of tangent, okay? So for this derivative to exist, the slope from the right and left has to exist. Okay, so hopefully this helps you differentiate the two different kind of limits here. All right, I'm just going to take a break right here on this one.